Okay, so like I said, this is going to be lesson 5.3. And the title of this one is called The Definite Integral. The definite integral. So there's two types of integrals. One is called the indefinite integral, and one is called the definite integral. Okay, what we were doing when we were dealing with the antiderivative, and we called Brooks the sea monster, that is an indefinite integral because I don't know where that antiderivative exists. The arbitrary c says it could be anywhere. It's a constant. It could be floating at any place on the y-axis, right? The definite integral nails that down. It tells us exactly on what interval we're talking about and where it's going to be located. Okay? That's the difference. So for this part 5.3, I wanted to look with you at page 415. And it has the definite integral in the form, okay, so that's this business, on the interval from a to b. These two thingies right here, a and b, those two numbers are called the limits of integration. And you just saw that in physics, right? We just looked at how do I integrate from x equals 0 to x equals 3. Or x equals, I think the one we did was 0.08 to 0.10. Those are called the limits of integration. That's the interval. And so in the table business that we looked at, we saw on the interval from 0 to 8. That was the example we worked yesterday several times. On the interval from A to B, right? That's equal to the Riemann sum in limit notation. The limit as the number of partitions goes to infinity from the first rectangle to the nth rectangle of the rectangle's height times the rectangle's width. Okay, and you need to be able to dissect that limit and understand exactly what it's talking about. In our notes and everything we did, we had x sub k. Here they're having x sub I, where they're dealing with the i-th rectangle instead of the k-th rectangle. Okay, by that point, I think it doesn't matter. Okay, we understand exactly what's happening here, though. Height, width, add them all up, get a bunch of them to be more accurate. Otherwise, you could write it as the limit as delta x goes to 0, right? Take the width, very small. If I have hairline width rectangles, I got a bunch of them, right? It's the same idea. So the closer look here is really what I wanted to see. It says the precise meaning of that limit that defines the definite integral is as follows. So for every number t equals 0, there exists an integer n such that this, okay? The norm of the partition is defined to be the maximum width of all subintervals. So if I take that width, which would be delta x, to 0, I get the same idea as taking the number to infinity. Okay, so p being delta x. If I take that delta x to 0, I get the same information as if I took the number of rectangles to infinity. The symbol, this elongated S business, which if you check out the front of your textbook, everybody flip your front of your textbook over. You see it? It's on the violin. Oh, it's beautiful. That elongated S is made by Leibniz. That's called the definite integral sign. Okay, so that's where that symbol is coming from. It's kind of an elongated limit of sums. So we're taking this limit of sums business and we're just using this symbol to say that. It's the same thing. It's just a different notation. Okay. The values a and b are called the limits of integration. We just talked about that. A is the lower limit, so on the left side. B is the upper limit, the upper right-hand boundary. Okay, so always from left to right, from A to B. Hello, Lily. For now, the symbol dx has no specific meaning by itself. So rather just let it be all one symbol representing the definite integral. The dx simply indicates that the independent variable is x. So we're talking about in terms of x. If I had been talking about f as a function of time, I might have f of t dt. Okay, so x is just telling me what's my variable. The procedure for calculating the value of the definite integral is called integration. Integration, okay? That's what we're doing. The integration is different than the anti-differentiation because anti-differentiation isn't evaluating anything. It's the plus C business out to the end. You know, we're not plugging in any numbers. We're taking the function and we're finding its antiderivative. Integrating is different than that because we're finding the antiderivative and then evaluating on these limits of integration. So it's going to be a little bit different here. Okay, guys, if you're sleeping, I'm going to make you stand up and do jumping jacks. Get it. Lick your eyeballs. Get it together. Okay? All right, so the definite integral is a number. It does not depend on x. We could use any letter in place of x without changing the meaning or the value. Okay, so f of x dx, f of t dt, f of r dr. Are y'all seeing all of those things right here? Okay. This business is a Riemann sum. The limit notation is Riemann sum on steroids. Okay, we calculated Riemann sums yesterday. So that's why I'm not super interested in getting into the weeds of this text because we've done this already. Okay, turn your page over to page 416. Page 416. Note figure 5.27, kind of in the middle of the page. What kind of Riemann sum is that one? Midpoint. Good. Can you tell? Because all of the rectangles are heighted based on the midpoint value. Yeah? Okay. Look at figure 5.29. The Riemann sum is the areas of the blue rectangles minus the areas of the green rectangles. And I think I took a picture of that. Yep. Okay. So here, when we take the integral, we're dealing with the net area. It's the difference of the two areas. So if you have an area above the x-axis, that's going to be positive. The area below the x-axis is going to be negative. Okay? So let's say that I am integrating acceleration. Integrating acceleration. If the area under the curve is positive, which would be velocity, what does that tell me about the velocity? What's the car doing? Okay, going to the right, going to the east, going up, north, right? So if velocity is positive, if the area under the acceleration curve is positive, that tells me which way the velocity is. So if the area under the acceleration curve is negative, now what's my particle doing? Going down, could be going left, west, right? How do I calculate speed? What's the difference in speed and velocity? Direction, right? Lack of direction. So speed, the velocity is going to be the net curve, the net area, right? Speed is going to be the absolute value. It's not going to care whether it's positive or negative. It wants an overall absolute value. Same thing works if I have a velocity curve. If I'm looking under a velocity curve, what am I calculating? Position, displacement, right? If the area under the velocity curve is positive, displacement is positive. If the area under the curve is negative, displacement is negative. You with me? Okay. What if I take the absolute value of the area under the velocity curve? Absolute value. Now what am I talking about? Not displacement, but distance. Distance, because distance doesn't care which way. You following? Okay, so this is a net change idea. All right. Yeah, I think that's all that I wanted out of that page. Look at the bottom of Theorem 3 on page 417. turn over and find theorem 3 at the bottom? Do you see how they're getting delta x equals b minus a over n? And x sub I or x sub k is a plus delta x times, okay, that's exactly what we've already done. So I'm willing to move it on. All right. Example 1 at the top of page 418. Example 1 at the top of page 418. Nope. If we just dissect that just a second, it says write an integral expression for this limit. So let me write this limit down, and we're going to hack this out really quickly. Our limit is as n approaches infinity from I equals 1 to n. And the function here is x cubed plus x sine x delta x. If we were to write this in an integral, okay, the first thing we would do, so it says write it as a definite integral on the interval from 0 to pi. So the first thing we would do is do what? We would have this. What are my limits of integration? From 0 to pi. And what's my function? Good. And what's my variable? X, right? So we're going to have dx here. So that's the conversion. No, we didn't evaluate the integral. We're not trying to solve anything. We're converting from limit notation to integral notation. Okay. Any questions on that? That's okay? All right. So let's jump on to example 2. Example 2 says evaluate a definite integral. So let f of x be x cubed minus 6x. Let p be a regular partition of 0 to 3 with 6 subintervals. Find the value r sub 6, which is a Wright-Riemann sum. So this is exactly what we did yesterday in the tables. But instead of having a table of values here, we've got a function. Let P be a regular partition, meaning equal width, on 0 to 3 with 6 subintervals. What does that mean in English? 6 rectangles on the interval from 0 to 3. So what's my delta x going to be? Half. Okay. So while we're, I think it's helpful to draw a picture. You don't have to draw a picture, but I like picture. 1, 2, 3, 4, 5, 6, 8. We did it. I can split 0 to 3 6 times. Yes. We want a Wright-Riemann sum. This is why I think the pictures are handy, because they make me understand what values I'm actually looking for. Yeah, so I'm not going to be interested in f of 0. Are you with me? Because that's going to be on the left side of the rectangle, and I don't want to know what's happening on the left side of the rectangle. I want to read f of 0.5. What is f of 0.5? And then that'll give me my rectangle. Y'all with me on that? So really, you don't have to draw the whole picture. It may not be helpful for you. You may not need it. But it is good to at least know I got a bump to the right. Okay, so the Riemann sum here is going to be delta x times f of 0.5 plus f of 1 plus, and I'm going to really wish that I had started mine way over here. Delta x times f of 0.5 plus f of 1 plus f of 1.5 all the way. Do I want the value at f of 3? Yes, because it's a right Riemann sum, I want that one. If it was a left Riemann sum, I would have used 0, and it would have stopped at 2.5. Yep. Good. Okay, so how do we get these f of values? Yeah, you plug into your function. Plug into your function. So this is going to be half times f of 0.5, which I don't know. Do we want to spend time doing this right now? Not so much? Okay, so out of your textbook, we can read those values. F of 0.5 is going to be negative 2.875. F of 1 seems to be negative 5. So minus 5. Minus 5.625. Minus 4. Plus 0.625. Plus 9. Again, I'm reading these straight off the textbook. So once they compute, they get negative 3.9375. That's the Riemann sum with 6 subintervals. Now, does that tell me an accurate, exact picture of what's happening under this curve? Is that the area? No, that's an estimate. Look at the picture on page 419. Everybody find that picture on page 419. I didn't take a picture of it. Do you see that that's decent at best? That's the best you can do if you're taking partitions that are half a step wide. You'll see it? Put your finger on that picture. Everybody. You see it's not accurate? What would be better? Oh, okay, a trapezoidal might be better than this, right? What would be even better than a trapezoidal sum?
A left-hand?
Okay, maybe a left. What if you had 11,900 partitions? Wouldn't that be better?
Yeah.
Wouldn't it to integrate be better? Okay, that's the point. That's what we're getting at here. All right, so let's go on to the next page. You see the picture at the top of page 420? That's exactly what they're saying. If you could smooth it out, that would be more better. I want to bring you back to this guy. Oh, he went away. That Pokemon picture that I had yesterday where the edges were really rough, but we could make it better if they smoothed it out. Okay, that's the idea. Example 3 says, set up but do not evaluate an expression for the definite integral of this. So let's do that one really quick. Example 3. Set up but do not evaluate an expression for the definite integral of the integral on 1 to 3 of e to the x dx as a limit of sums. Okay, so how do we write the limit of sums given an integral? First thing I want to do. Okay, the limit as n approaches infinity of the summation from k equals 1 to n. What's my delta x in this case? Yeah, 3 minus 1 over n, 2 over n. What is my x sub k? Okay, starting with a. Remember, it's a plus delta xk. So 1 plus 2k over n. Where a is 1 from that integral. What's f of x? Just f of x equals e to the x. So what is f of x sub k? E to the 1 plus 2k over n. Okay, so my limit is going to be f of x sub k times delta x. So I'm having the limit as n goes to infinity from k equals 1. That's the first rectangle. Now, is this, question, is this limit that I'm writing right now, is this a right-hand limit or a left-hand limit, and why? From k equals 1 to n. We haven't talked about this. It's right. How do you know it's right hand? Because I'm bumping to 1 from 0. So this is saying from k equals 1, from the first position. If it was a left-hand position, left-hand integral, it would say, or a left-hand limit, it would be k equals 0. Yeah, so these have been always right hand that we've been writing. Yeah. Okay, anyways. Of e to the 1 plus 2k over n times delta x, which is 2 over n. Now, we could compute this whole limit by hand, right? It says use technology to evaluate this expression. You would have to have a CAS, some kind of algebraic system that was just Jim Dandy, okay? Look on the page 421. Can you flip your page over to page 421 and look at it? You see this business that they've done on their calculator? It is a whole lot. Or there's got to be a better way. That's the integral, right? So we're still moving out of this idea of the Riemann sum. Thankfully, we're not here for 6 weeks. You remember at the beginning of school, before I let you take the derivative, I made you do limits for 6 weeks? Okay, we're not doing that. We're moving on. Moving on. So flip the page over to example 4. This is kind of the last ditch effort to solidify this. It says this is the key to a deep connection. They're serious about it, right? It is important to connect or associate a Riemann sum with an appropriate integral. Write the definite integral equivalent to this limit. So one last try at this. One last time. We've got a sum, and our job at this point is to write the integral that would represent this sum. Okay, so y'all are already going to work. Talk to me. What are you doing? Writing it down. Okay, writing the function down. Sorry. Get a little bit excited. You don't know how much I like this.
I was like, just writing it.
I'm just writing it down right now. Just hanging out. Okay. What do you know about delta x? Delta x is, okay, so b minus a over n is 2 over n. Look for some a value within this function business. Does any a value pop out at you? I think it's the 1. Okay, that's just some guts, some intuition. I feel like this 1 right here tells me that a equals 1. So if that's the case, my limits of integration are going to be what? 1 to 3. 1 to 3. What? Just out of thin air. Okay. So, Noah, we're looking at this function right here. Do you see the 1? That kind of stray 1 business that doesn't feel like it's a part of delta x? That's how I feel like it's a. Are you with me? It kind of is nested into the function. Feels like it's part of f of x, but it's not delta x. That means that a is 1, and if b minus a equals 2, then b must be 3. That's the only way I subtract and get 2, starting at 1. Okay? It feels like f of x sub k here is that natural log of 1 plus 2k over n. Doesn't it? So what do you think f of x might be? Natural log of x. Dx on the outside. We got it right. Okay. So that's kind of the finale. That's the last ditch effort to understand how are we getting from the limit notation of the Riemann sum into the integral. Any questions on that at all whatsoever? Anybody? No. Okay. All right, so we're going to look at one example before they let us actually start doing the thing. This is example 5. Okay, how to do it in 2 pieces here, sorry. Now, play right. There we go. Evaluate the following definite integrals by interpreting each in terms of areas. So far, they haven't taught us how to integrate yet. So you can't use that, you little physics babies. You can't do integration yet. We're supposed to look at this. It says by interpreting each in terms of their areas. So we're thinking geometry. Okay? Let there be geometry in your little brain. This one is actually, I have seen this before on a practice AP exam. Okay? They expect you to know this, which is a scary thought to me. Let me introduce you to my friend, the circle. You know circle formula? Did y'all do geometry at some point in your life? You little AP calculus kids? Okay. In geometry, you should have learned area of a circle or the equation of a circle. Y squared plus x squared equals r squared, or x squared plus y squared equals r squared, where r is the what? Radius. So if I wanted to graph a circle of radius 3, my equation would be y squared plus x squared, or x, I got those backwards. It doesn't really matter, but it's supposed to be x squared plus y squared equals r squared. If I'm graphing a circle of radius 3, then my equation here is x squared plus y squared equals 9. Okay, y'all remember that? Did you learn that before? Nod, yes. Yes, you did. Nikki did, because I think geometry may have changed since you guys were in geometry. So this function up here, the square root of 1 minus x squared, they want you to realize that that's the equation for a circle. Now, how did they get that? Well, if I have x squared plus y squared equals, let r be 1. Radius of the circle is 1. And I solve this equation in terms of y. I'm going to swing that x squared. Y squared is 1 minus x squared. Y is plus or minus the square root of 1 minus x squared. Y'all with me? So y equals the positive option of 1 minus x squared. Well, that graphs the top half of this circle. Y equals the negative option. That graphs the bottom half of same circle. Okay, so when you roll up on this business that says the square root of 1 minus x squared, your brain needs to think circle. Circle of radius 1, because 1. Okay, all right. So now that we know that, we're on the interval from 0 to 1. This is positive square root, so only top of the circle. Top of the circle should go from negative 1 to 1. But I'm only interested in the area from 0 to 1. How do I find the area under this curve? 1/4 of the area of the circle. What is area of a circle? Now here's where things get really hard. Area of a circle, pi r squared. We want the area of the quarter circle. So we'll have 1/4 of pi, and what's r? 1. How do you know it's 1? Because it's 1, this one right there. A 1/4 of pi times 1 squared is going to be pi over 4. That's the answer to this question. Is the area under the curve. So the integral on the interval from 0 to 1 of 1 minus x squared dx is pi over 4. Isn't that cute? Do y'all feel great about this?
What did you multiply?
Oh, that's 1 squared. R squared. R being 1. Yeah? No calculus needed. Understanding conceptually, but you can geometry this guy. Okay? And in fact, that's the expectation. When we start doing this later on and we actually start integrating by hand, you will realize that this is not possible by hand, not by any rules that we understand. So the expectation here is I recognize circle and I geometry. Okay? Okay, on to the next. This will be our last example for today. We are going to integrate from 0 to 3. The function is x minus 1. X minus 1 dx. Find the area under the curve. So what does your little gut tell you to do? Graph it. Graph it. Look at the picture. Look at the picture. What is this function? This is x minus 1. Talk to me about this function. Y equals x minus 1. It's a linear function, okay? Slope of 1, beginning at negative 1. So I'm going to put my B on my graph. Rise 1, run 1. Rise 1, run 1. Do I just do this indefinitely? Get it? Indefinitely? Oh, no, I do it definitely only from 0 to 3. Did y'all see that? Did y'all see what I did? I'm amazing.
Oh no.
Rise 1, run 1. Rise 1, run 1. That's beautiful. Now, how might we compute the area under this curve? Well, there are some things to consider. Some of them are negative. This little area right here under this part of this curve is negative. And this area over here above the x-axis is positive. So the integral is the area between the curve and the x-axis. Okay, we missed that in physics early. Is the area between the curve and the x-axis. So I'm going to have this area of this blue circle, let's call that A1 circle, triangle. I never say triangle. Triangle's like not the word for me. Minus the area of the red triangle because it's below the x-axis. How might you find the area of the blue triangle? Oh, half base times height. What's the base of the blue triangle? 2. What's the height of the blue triangle? What's f of 3? 3 minus 1 is 2. Also 2. Okay. Minus, what's the area of the little red triangle? Half its base, which is 1, times its height, which is also 1. I'm way out of room over there. I think my first halves cancel. Half and 2. So I'm left with 2 minus a half. 3 halves. 1.5. So the integral on 0 to 3 of x minus 1 is 3 halves. That's what we're doing. All right? Interesting. Yay. We like. Tomorrow, we'll start using the calculus. We'll actually get into like the mathematics of that. Okay?